Okay, I think we are ready for the fourth talk for this morning, Professor Valentin Ovsienko. I'm not sure if there's a change in title. It used to be non-commutative elliptic Poisson structures.
No. The title was always the same.
Okay, well, it's shadow sequences of integers, it seems.
Yeah.
Thank you.
I apologize if Vale changed it, but it's my fault.
Okay, please go ahead.
Okay, so thank you. Yeah, thank you very much for this possibility to talk here. I would much prefer to be with you in personally, but unfortunately it was not possible this time. Okay, so my goal will be to tell you something that looks quite crazy. So suppose you have an integer sequence, a n, and so I will show you that in many cases one integer sequence can hide another one, its shadow, another integer sequence, which I will denote alpha n. It's actually not a one-to-one correspondence, so one sequence can have several shadows. Okay, and so I will give you many examples. And one of the sources of these shadow sequences lies in is related to cluster algebra, and more precisely in cluster super algebras. Okay, so let me recall that when Fomin and Zelivinsky developed the theory of cluster algebras, so one of the motivations, among many other motivations, one of them were integer sequences. So the famous paper which is called Laurent phenomenon, which is the main property of cluster algebras, actually it was to prove integrality of some sequences that are called Somos or Gale-Robinson sequence. So they proved conjectures of that several sequences were integer. Okay, so now I will, the notion of cluster superalgebra was discussed yesterday in a series of very nice talks by Ashish, by Nick Ovenhausen. So Anton Seitlin, it's not yet completely clear what it should be, but I'm sure that there is no just unique way to define a super analog of cluster algebra. So I will give you one such definition. Okay, and I show you that it also will lead to integer sequences. Okay, good. So now, first, I will very briefly recall you that what is a cluster algebra. It was also already discussed. So actually, the algebra itself, algebra can be somewhat misleading. It's rather one talks not of the algebra, but of coordinate transformation. So you have x1, so on, xn, and coordinates, and you make an infinite series of coordinate transformations. Or if you prefer, you can say you have an infinite series of maps. So these maps are usually called mutations. And the definition of such a series of transformations will be combinatorial. So you put your variable x's, you put you label by your variables vertices of some oriented graph, which is should be called a quiver, because this is how it's called in the representation theory. Okay, so now the transformation of every coordinate will be given by a similar way. So it's a sum of two monomials, sum of two products of x's, and this just the first family is just the axis which related to the vertex xk by ingoing, and the second group is just outgoing errors. Okay, and then you divide by your initial variable x. Okay, so the quiver itself, the graph, the quiver will also be transformed. So if you mutate at this chosen vertex, then first of all, you choose the orientation of all arrows connected to this vertex, and then you also add a new vertex that which is a shortcut path from this to this. Okay, is it clear? I hope it is clear. So this is the definition of what we call cluster algebra, and unexpectedly this is something extremely universal. This notion is very universal, so it includes all the Plücker relations in the Grassmannians. It also gives very nice coordinate system on Lie groups and so on. And so you actually it's also is very useful in the theory of integrable systems. So this cluster algebra theory really became some extremely important part of mathematics today. Also, I need to say that actually these rules of mutations of quivers appeared simultaneously in mathematics and in physics. And in physics, it is called some Seiberg or Seiberg-Witten duality in particles physics. So it is really amazing. Okay. Well, very good. Now, what is a cluster superalgebra? So clearly, we need to deal with two groups of variables, even variables as before, and now we add some Grassmannian variables that anticommute with it's so the anticommute. Now the so why I'm going to describe unfortunately it's half of the story. We will only define mutation of even variables, just as it was in my previous slide, but the Grassmann variables will participate in this formulas of mutations. Okay, so the notion arose to understand so the notion of freeze patterns, which was freeze patterns is a very nice object in combinatorics, which was invented by Coxeter in 70s last century, and it is related to continued fractions, and actually it's also related to the Grassmannian of two planes in n-dimensional space, G2n. So what is this cluster, this super freeze pattern? It is a variety in the Grassmannian of two planes in n/1-dimensional space. Okay, so it was defined by Sophie Moryezhnu, Sergei Tabachnikov, and myself in 2015. And that was the year when I started to think of the class, how to generalize the notion of cluster superalgebra in order to include this super freezes into it. Okay. Then, so it was not completely successful, but then later on with Mikhail Shapiro, we continued the work. Okay, so now what is it all about? So first of all, underlying story is exactly as it was in the cluster algebra. So we have our even variables label vertices of some oriented graph as before. Okay, so xi, xj. So i's and j's are groups of variables, income related, connected by income or outgoing arrows with x. But now we extend this quiver. We add some odd variables here, some xi, i's, and xi j's. But so what now? Surprisingly, we will not have a quiver anymore, because I don't want to count the arrows from odd variables to even variables, but I count paths, the paths from say xi I connected to xi j through even vertices. So it's a two path. Well, in mathematics, such a hybrid structure, you have some arrows, but you also have paths. It's called a hypergraph. It's a terrifying word, hypergraph. When you not only count vertices and arrows, but also some paths. And this is extremely important. And that's probably the crucial property.
Valu, may I ask you?
Yes, please.
Yes. But you still have. Why do you say that you don't have a quiver anymore? So you still have a quiver, but you consider some extra piece, like these two parts.
So I called extended quiver, which is actually not a quiver, but hypergraph. Okay,
but you picture the quiver. So that's
no.
But
no,
you picture
because there is you don't. There is no meaning to take just one arrow here and one arrow here. You take the whole path. It's very important. For instance, if you have a multiple.
No, I see that. So, but you picture. I mean that you just interpret your picture in different way. But you picture the same quiver, but you just use it differently to the standard way. No.
Look. If you have multiple passes like that, then this counts by two, because you xi I is connected to xi j by two passes.
Yeah,
okay?
I see that. I see that. Well, I see that. So, but the picture is just the
arrows,
same.
then it is 4. In the usual cluster algebra, it will be 4, because 2 times 2 is 4. Understand? And this is completely it changes the computations very drastically. So it was the main difficulty to understand this story. Otherwise, it doesn't work. Otherwise, we will have many restrictions to the quivers, and then it will be well. It's very important, because in the formulas you will count this situation as 2. Multiple passes will be counted just as passes, not as multiplication of arrows. Is it understandable?
Vale, no, I just my question was quite naive. So I was simply saying that you have just the same picture, but you use it for your definition in different ways because you don't consider you have on the picture these arrows, but you consider the two paths made of them. Is it right?
Well, maybe it's a kind of. But in the computation, you should be
In the computation, yes, yeah.
Yeah. Well, the picture, I don't know how to draw the picture. Well, okay. Anyway, so well, this doesn't mean either that the odd variables comes by pairs, because every variable can be connected with many other variables. So the only thing is prohibited is you cannot simultaneously have two passes differently oriented. Then you cancel. When you can cancel, you cancel them. Okay, it's just the same story as in the usual situation. Okay, now mutations. First of all, yeah. So we need two notions: the mutation of the variables, the exchange relations for the variables, and also for the graph. So let me first start with the formula. So xk, every variable xk will be transformed in a similar way that it was in the classical algebras, classical cluster algebra. Okay, so you take the product of let me start from outgoing. K gives j, so xj plus the product of going x's xi, right? I connected to k by going arrow, and here we will add another product of some odd variables, and it will be 1 plus xi I xi j. Okay, and the product is taken over these two passes. So I connected to k, connected to j, and the orientation, of course, will change. So if you change the orientation of these two passes, it will change the sign because they anti-commute two variables. Okay, so here you have.
Valia, excuse me. So do you have any signs? So have you missed plus? You said another product. It just plus the third product.
Times.
At times.
Yeah. So here you modify by multiplying by this.
But this I has not. This first I has nothing to do to the other I. You have I and j in the second product.
Oh my God. Yeah.
So you just call it j and L or something.
Yeah. Yeah, you should change. Yeah, so it's yeah. Thank you. Yeah, yes, different eyes. Okay. Yeah. Okay. And now the quiver. It's an important story. So we mutated xk. So what happens to the quiver? It was hypergraph. It was something like that, right? So first, you change all the orientations at x as it was in the classical case, all the orientations, and then this vertex, only this vertex, which is connected by outgoing arrow, will receive what was here. So let me add. So the new two pass is here, and also as it was in the Fomin-Zelinsky case, you also have this new arrow which will be added, and that's it. So this is the definition. Unfortunately, I don't know how to mutate odd variables, and even so with Misha Shapiro, we don't even know if this makes sense in this situation. I think it should make sense because in the freeze pattern we have much more odd variables than the dimension. So there should be some formulas for mutation, but we were unable to find them. Okay, the special case, well, maybe I will very briefly say, when m is the number of the odd variables. If you only have two odd variables, say psi1 and psi2, then for every even vertex, the only thing we should know is how many passes are connected. So we call it. So we have an integer here, an integer wk weight function. Weight, and means how, with the orientation, of course, how many passes through xk, okay, connecting xi1 and xi2, and now the formula will simplify. So you have the usual mutation of your underlying quiver. It mutates according to Fomin and Zelinsky, and of course the axis will mutate with this weight function will participate, but the weight function itself will change in the following way. So at the point k, it will change the sign because the orientation is changed, right? And then at the point connected by outgoing arrow, it will become the new weight function is the what it was plus the number of arrows connecting. So B, usually called B, the matrix, exchange matrix B from K to J times WK. And actually, what is important here is that was the observation of Misha Shapiro, that what is written here is the dual to the very famous Bernstein Gelfand Ponomarev functor. So it's dual Bernstein Gelfand Ponomarev functor, what we get here in this special case. Okay, yeah, so now just I will show you many examples of what will happen to integer sequence. But so the idea, what will be this, what I promised you, the shadows of integer sequence. So suppose you have an integer sequence an. By the way, integer sequences are everywhere in mathematics. So it's what we are trying to do is a kind of very universal thing. But so I will only consider sequences that are given by some initial conditions together with relations, which will be given by some algebraic expression, so rational function or polynomial. An plus k depends on an sorry, to n minus k plus k minus 1. Okay, so n consecutive terms define n plus 1, the term number n plus 1. So there are, of course, thousands, hundreds of thousands of known sequences satisfying this kind of relation. So there are two ways to create the shadows. First one just has nothing to do with the cluster algebra, but it is super algebra here. So instead of you take, instead of an, you consider an expression of this form, an plus alpha n times epsilon. Epsilon actually morally it corresponds to psi1 times psi2. So it's some nilpotent object. It's now both a n and alpha n are integers. Okay, so it looks like Gaussian integer in complex. If epsilon was not not an important, so
integer dual numbers. Well,
so
integer dual numbers.
Yeah, exactly. So this is called dual number. It was introduced by Clifford, and it's one of simplest Clifford algebra here. Okay, and then you substitute this a into the relation, and then it will determine you. Well, of course, we need to choose. We need to choose a clever initial condition here. Okay, then you will obtain the second sequence. And so the second way is indeed will be indeed related to the cluster superalgebra. It is so, but I won't explain it here. You will modify it. Yeah.
How did you calculate alpha n in the first case?
You simply substitute to the relation. Instead of a, you substitute capital A, right? You substitute this expression to the same, exactly the same relation. I will give you examples. I will show you examples, and this will determine alpha n, provided you have some initial condition. Of course, you need to choose initial conditions. Okay, so let me give you examples. I have maybe 5 or 10 minutes. I will show you examples, and let us start with the best possible, the most honest integer sequence that consists of all positive integers. Okay, so what about this shadow? It turns out this is already interesting. So it's already an interesting example, because what I claim. Well, claim it means it's something. It's not a theorem, because of course I'm cheating, because otherwise anything can be called a shadow. So I will show you that a shadow of this sequence is these nice sequences of tetrahedral numbers. How should we proceed? So first of all, we don't take the relation a n plus 1 equals a n plus 1, because it's not cluster. So the choice of the relations is, so it should be as close to cluster algebra as possible. So here we have minus sign, but it is otherwise it is very, very cluster looking relation. You see n plus 2. So this is exchange relation for a n. Okay, now when I substitute, instead of a n, I substitute this dual number a n plus alpha n epsilon, then what we get for alpha n is this. This is the relation. And if we choose the initial condition 0, 1, then we have this. Well, what I need to add, that it's absolutely, well, it's at first glance, it's not clear. Why should this sequence be integer? Because we divide by n every time. And this is the Laurent phenomenon, that manifestation of the Laurent phenomenon. So if you take another initial condition, say 1, 0, then you obtain the more or less the same sequence, but with opposite sign. So this is why I call it shadow of. Okay, let us take just another example. So Fibonacci. I claim that the shadow here is the convolution of Fibonacci with itself. By the way, in the previous case, the tetrahedral number was the convolution of the natural sequence with itself again. Okay, well, the same story, but instead of so here we take just this Cassini identity for Fibonacci, this square. Okay, now a much more sophisticated, a much more interesting example, which is indeed very interesting. The Markov sequence of Markov numbers. So one statement which is well known and due to Markov is that every solution to this Diophantine equation, which is called the Markov equation, can be obtained from the initial solution 1, 1, 1 by this series of mutations. What you see here is, of course, the exchange relation. And this is why Markov numbers are connected to cluster algebra. And the quiver that we can associate to Markov number is this. So we have three vertices labeled by A, B, and C. Okay, that connect, which every one is connected by two arrows with the other. Okay, and then when you mutate, the orientation will change, but the quiver remains the same. This is the just the mutation, and the exchange relation is this. Okay, so this is why it is connected to the cluster algebra. Now, well, I briefly recall that Markov number form a tree, so infinite binary tree. At every vertex, you have three regions that you should label. ABC will label the regions at every vertex, and this is the mutation, which corresponds to this local picture. Okay, now the Markov tree is here. So you start from 1, 1, 1. Then the first mutation transforms 1 to 2. Second mutation transforms 1 to 5. And then you have choice. 2 becomes 13. 1 becomes 21, and so on. So here you have, of course, Fibonacci branch of the Markov tree, and here you have another classical sequence of numbers, which is called Pell number, also known to ancient Greeks as the Fibonacci sequence, of course. Now, what is the shadow? We just substitute to the same mutation relation dual number expressions, and then we get this. Once again, the Laurent phenomena will guarantee that the sequence will be in integer, and so you have every Markov number will appear with its counterpart, with its shadow. And so if you look now at the Fibonacci branch, though this is a known, what we get is a known sequence. It's a very beautiful sequence, convolution of odd and even Fibonacci sequences together. But otherwise, other sequences are not in the encyclopedia. So, for instance, this Pell dual, this shadow Pell sequence is not in the encyclopedia. Okay, now one can prove the following, that in the talk of Anton Saintlin, there was a version of Markov super equation, which was more complicated and I think a little bit more ugly. So here we have this. This is the deformed Markov equation. You just add one term here. Okay. Well, and now so I will to finish my talk, just the one more example. So this is what happened. What was one of the main motivation for Fomin and Zelivinsky. This is the so-called this Somos sequence. Look, so the Somos sequence is determined by 4 initial numbers, which is chosen equal to 1, And then the relation recurrence is here. Once again, so the well, first, so Sommers invented his sequencing in 80s, and there are several others. Sommers, this is called Sommers 4. There are Sommers 5, so some other sequences. And well, there was an activity around David Gale. People proved that this sequence is indeed integer, and so it was generalized Gale-Robinson sequences. It is actually the quiver connected to underlying quiver for this sequence is more sophisticated than we saw for the Markov number. You see, so it is quite amazing quiver with 4 vertices. 4 vertices because we have 4 initial conditions. This is clear. And now what happens if we mutate at x1? The quiver remains the same, but it will rotate at 90 degrees. And it's called so-called one periodic. So one can find it in the paper of Ford and Marsh, and also in the book of Robert Marsh at one of the first pages. Okay, so you have 2 choices. You have you can choose one or orientation or the opposite. And now what happens? There are 2 extended quivers, which is also one periodic. Only 2, exactly 2. So for each choice of the orientation, there is only one. So there is unique way to extend this each of these quivers, so that it also rotates when you mutate according to my rules that I explained you. Okay, and what you get here is 2 deformed sequences. So instead of so if you drop this epsilon, if you epsilon equals 0, then you get the Sommers relation. But now what happens is you deform it. You deform it. It gives you some deformed sequences, and you can, well, the sensible way to choose the initial condition is 0, 0, 0, 0. So this is what the shadow. We have 2 shadows here. Okay. Yeah, so I gave you examples, and well, the story is not, of course, finished. So there are some references that I wanted to show. That was my initial preprint that remained unpublished. I think the humanity was not ready to accept. Then the case of 2 odd variables was completely developed in this preprint, and so this is how we worked with Sergei Tabachnikov on deformed this shadow sequences of Sommers and Gale-Robinson. Then with Misha Shapiro, Misha understood how to this should be correctly generalized for many odd variables. And okay, so this is what I wrote for mathematical intelligence about shadows. And Andy Hohn connected the sequences that arise in this as shadows of Sommers to beautifully connect to elliptic curves. Okay, so thank you very much for your attention.